be groups. So then we can consider G underlined and H underlined as categories with a single object. We compute what is the category of functors in this case. Yeah. So in the, for example, in the G underlined, we have one object, and the maps from this object to itself is just the group G. In this case, you need to compute the category, so you need to compute what are functors and natural transformations between functors.
So maybe еще раз у нас категория отдельный элемент, не в смысле, то есть как бы группа и Um, so we need to find functors from these categories. I think that the first category can be described as with picture, like one element group and all arrows with group into itself. Что?
In the center, I think there should be just a star, right? So there is only one object, and the maps from the object to itself, as many maps as you have elements in the group. I mean, the description I would write, which is probably what you meant, you just take a star, and then you have this.
То есть мы берем один элемент и
There is one object.
И его ну, его стрелки это группа G.
This is exactly what I wrote. You have one object, and if in this category you compute maps from this object to itself, you get exactly the given group G.
It is Y или G?
G1, G2.
Okay. So a functor is it is map on objects, but the map is trivial. We send in one element to one element. And it is maps on arrows. That satisfies two properties, like where unity of the arrow goes to the unity of image of object. So I think I can call them star 1 and star 2. And so any map from G to H that satisfies these two properties will give us an answer. So it's like homomorphisms of groups, but yes, it's like homomorphisms of groups, no? Because with two are given properties, and I think that we need to check that we have inverse object in image.
Why? It's not part of the definition of a group homomorphism. I don't understand why you use this.
В смысле отображение, сохраняющее групповую структуру.
Yeah, but this is precisely what you wrote in the third line. You map compositions to compositions. In this case, compositions are just products in the group. So you map
Yes,
the products.
yes. So that it is.
Yeah. So any natural transformation is precisely the same thing as a group homomorphism. But it's not the first part of the problem. The second part of the problem is to find natural transformations.
Так.
Все-таки f как определяется на G? Ну, по определению функтора так должно быть, вот, то, что написано, но как мы его определили, мы же должны явно как
Ты пишешь гомоморфизм группы, просто у тебя
Да.
морфизм приходит в морфизм, соответственно.
ну, если у меня какие-то соотношения в одной группе есть, а в другой нет таких соотношений, ну, их тогда не будет.
Я думаю, this is a functor, so this is a map on objects, and we also know that there is a map on the sets, or on the home sets, right? So in this case, this is what we have, right? Just by definition of functor. This we can identify with the G, this we can identify with the H. So there is a map from the group G to the group H as a sets, and then we have these two additional requirements that this is a functor, which precisely means that identity goes to the identity and composition is sent to the composition. So that's a group homomorphism. And if you have a group homomorphism, this is the same thing as a functor.
И нам нужно найти естественное преобразование между функциями, да? Мгм.
Or just by the definition.
Mhm.
Natural transformation. Right?
Yes.
So this is a group homomorphism.
Mm. I think not G1, but yes.
No, G probably not a good notation because we already used G for the group.
Yes. Oh,
H
H is also.
it's also
Chat. So we want
what's that map? H, Y1?
not. So we want this diagram to be commutative, and let's.
Can you specify what Y1 is? I don't quite understand this.
Y1 is arrow from the image of this. Arrow from image of star 1 to image of star 1, because we have only one object in category. All arrows are just arrows from this object to this object.
Well, this is not how we're supposed to write square for the natural transformation. On the horizontal lines, you need to apply functor F or functor L to some map in the category. I think what you need to do is to say something like Y1 is the F of G1, something.
Yes. Okay.
No, this is L.
Hmm?
L, not F.
Okay. And so the natural transformation is the map on each object. Yes. But this object is just star 2 because we can send star 1 only to star 2. And this object is also star 2. same reason. So the natural transformation is the identity map, I think.
Why? No, it doesn't follow this identity. Well, essentially, natural transformation is given by the components
Ah,
of the
yeah,
data, right? In
yes.
this case, there is only one component, but what is it?
It's it's just a map from star2 to star2. And we want this to commute with yeah, we wanted to commute it with elements of H.
Well, maybe it will be easy if I just ask you precisely. Maybe you can erase this. What if I want the formula? So suppose I can think about this as group homomorphisms, say F and G, from the group G to the group H, and then I can compute natural transformations within group homomorphisms, thinking about them as the functors, right? So what's the answer? This is something such by some conditions.
Mm-hmm.
Can we do this?
Yes. It is just an element of G of H satisfying this condition.
You just write formulas.
Such that
Yeah, so these are all elements in the group H such that in the sense they just conjugate homomorphisms, right?
mm-hmm.
So these are natural transformations in this case.
Yes.
Okay, thank you. Timofey, Maxim.
Timofeyev, да.
Okay, so let's go to the next problem. Categories, sets, and the opposite
Yeah. So, I mean, uh, assume that there is a functor which gives us the equivalence. Yeah. So then it should take, well, it basically, if we have an equivalence, we should equivalence should send the terminal object to the terminal object and the initial object to the initial object. So f of terminal object and sets will be just an empty set in object, so sets opposite, and f of an empty set will be just a singleton in sets opposite. But then let's consider just morphisms in sets between well, some set X, or any set, and an empty set. Well, unless X is empty, this whole set is empty. Then we can, it basically equals to the to morphisms as it's an equivalence of categories. We assume that this would equal to the set of all morphisms that's opposite from f of x to the f of an empty set, which is just a singleton. And that, as is just the category, as is just the opposite category, we reverse all arrows, and it's just the set of morphisms in sets from a singleton to the f of x. But in general, f of x, as it's an equivalence of categories, there must be some set like of 2 points. And, well, there are some morphisms, and it's not empty.
Yeah. So, for example, you finish this computation and write that the answer for this home set is just in bijection with the f of x, right?
Yeah.
So then we will get something that if we have an equivalence, and on any non-empty set, this equivalence is from empty set to empty set.
Последнее равенство как получилось?
Вот это все? Well, this is because it's just an opposite category. In opposite category, we reverse all arrows. So it will be arrows from the object, well, from this object to this object in general. Yeah.
Let's finish this computation. I think that's an important observation, that when you take a home from a singleton to any set, what you get is just this set.
Yeah.
So, and for this we can write something for two cases. This is empty, right? If x is not empty, and this is singleton again if x is empty. So anyway, so it's clear that we can have an equivalence of categories such that on any x which is not empty, the answer for the f of x is empty.
Yeah.
Почему есть противоречие между синглтоном, что не может равно f от x? То есть если x равно пустому множеству, почему противоречие?
На пустом сработает нам на всей категории. У нас получается, что если только у нас x не пустое множество, если мы меняем f, то получаем пустое множество. Явно это не эквивалентность. Okay, so let's upgrade this question a little bit. So the next variation is the following. R category the binary relations and the opposite category equivalence.
Может, пожалуйста, еще повторить, что за категория?
Бинарных отношений на множество.
Анархизм там какие вложения?
Бинарные отношения на множество.
Да. Объект это множество. Маркизм это множество, это бинарное отношение. Ну, соответственно, композиция бинарных отношений.
I mean, those are all problems from the Google class sheet, so I can go again, or I can just give someone else a try.
Let's give someone else a chance. But if you want the problem to solve right now, try to go back to the lecture notes and prove the two associativity identity for the horizontal product, horizontal composition.
Well, my idea is that these categories are obviously equivalent, and the functor that proves this simply mirrors the relationship. Namely, if we have some relationship between sets x and y, let's call it R, then, in the opposite category, we have like the same relationship as a subset of the product x by y, just mirrored. Namely, like R is a subset of x times y.
Is the transposition of the binary relation.
Yeah, okay, it's indeed a transposition, because if we draw it like this, x, y, and here we have some points that lie in R. If we transpose it, we get a relationship between y and x. So in this way, what is the functor I'm describing? Let us write it down explicitly. It takes each object to itself, and what does
You
it?
can just write this.
Yeah, okay. F from rel to rel op. F of x is just x, and f of r I'll write it this way to know that R is a relation between x and y, is just the same R, but as a subset of y times x. So it's quite obvious that, yeah, indeed, that this satisfies all the like conditions in the opposite category, like composition, for example, identity.
I think what is not completely obvious is that the compositions are mapped to the compositions.
Yeah, okay, let us write it down explicitly. May I erase this? So let us describe R as a composition of R1 and R2.
Когда рисунка загибается иксы, в случае, когда функтор действует на x, мы же имеем в виду, что мы должны пары отображать.
What, sorry?
Является парами.
Нет, тут действие на объектах, которые являются множеством просто, и действие на...
Yeah, the objects of this category are sets, and the morphisms in this category are binary relations between sets. Okay. So what does it mean in x and z to be related by R? It means that there exists y such that x relates to y and y relates to z. Well, but if we apply our functor, then z x, we know that it happens precisely like these two conditions are equivalent by the definition of functor. And well, if you write on the other hand this y we have to change obviously the direction of this composition, so it will be R will be a composition of R2 and R1 in the opposite category. So here we have Z R2Y and Y R1Z. Well, on one hand, we have that this happens at the same time as this, because this is equivalent to this, this is equivalent to this. So on the whole, this condition is equivalent to this condition. And well, since this is equivalent to this, equivalent to this, equivalent to this, we can draw the final equivalence that proves that compositions are preserved. I believe this finished the proof.
Yeah, for the identity, I think it's quite easy to understand.
Yeah, obviously the diagonal of the matrix stays the same under transposition.
Okay, so if we think about the categories as generalization of monoids, then we know that for monoids we can define the center of a monoid. And in fact, we can define the center of a category. So by definition, the center of a category, so this will be all the natural transformations. So between the identity functor to itself. So this notation is supposed to represent the fact that I take the identity functor and I take all the natural transformations from the identity functor to itself. So then the question is to show that the center of a category is some commutative monoid.
So to prove that this is a commutative monoid, we have to establish an operation, an identity, and so that it is indeed commutative. So no, the operation is obvious. It's just composition of natural transformations. Let us write down an example of such composition. So if we have a natural transformation from the identity functor to itself, it essentially means that for each objects x and y in C, we have a map like this, x, y, here x, y again, because these are the images under the identity functor. They are the same and just equal to the original pair of objects and the map between them. And let's call our first natural transformation alpha. So here we have alpha x, here we have alpha y. So this is like a typical natural transformation that lives in Z of C. If you have another one, natural transformation like this, it just means that we can continue this diagram beta x, beta y, and here again x, y, and f. So indeed we have an operation. To show associativity, I should continue this diagram for one more square, but I think it's obvious that this operation is associative. The unity of this operation, of this monoid, is obviously the identity transformation, and what remains is to show that it is commutative. So to see commutativity, note that we can take y equal x and f equal beta of x, because indeed beta is a map from the x to itself. In that case, this square we have transforms to x, 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 x again. Here we have alpha, and here we have beta x. And suddenly this shows that in this case alpha and beta necessarily commute. So like each pair of natural transformation actually commutes. So this is commutative. Okay?
So I don't want to do the following two exercises right now, but at least I can formulate them. So we know this is commutative monoid, but there are examples where you can compute those centers. For example, you can take the category of the left R modules and compute the center. And do you have the guess what this thing is supposed to be? Center of this category. The answer is very natural. Well, you can show this actually center of the ring. If you consider this as a monoid and the operation is induced by the product in the ring. So this is the first exercise that you can show. And the second exercise is much more interesting and much harder. So you can take the category of finite abelian groups. So this fin F is supposed to represent finite abelian groups. And you can try to compute the center of this thing. It's quite interesting computation, not elementary, but perhaps you'll find some p-adic numbers when you do these computations. So 2 examples. But what I want to do in the rest of today's seminar is to look at some examples of the adjoint functors. I think the several examples are quite elementary, the first several examples. So in the next series of exercises, one of the functors in the adjoint pair will be a forgetful functor, and essentially the other functor is something like a free construction, like a free vector space, free abelian group, or something like this. So let's start with something elementary that we already know. For example, you definitely have, say, forgetful functor u from the category of abelian groups to the category of sets. This functor just forgets that this set is an abelian group. And the natural question is, what is f such that f is left adjoint And it's from examples that we're going to consider, it's natural to expect that the left adjoint to the forgetful functor is something like a free construction. So this is why I call this F. Well, but I don't know why I call this U. This is just tradition. Well, I'm pretty sure that you can guess. We actually discussed maybe this a little bit a week ago on the lecture, that a free abelian group on a set S, this is just this abelian group, right? So by definition, this is direct sum of several copies of Z, as many copies as we have elements in the set S. So this is one example. The special, well, not special case, but a variation of this example will be free vector space. Generalization will be something like we have forgetful functor, say from the left R modules to the sets. Again, we have a polarity adjoint functors, free left module, and a forgetful functor. So this F on the S is just defined in the same way. Okay. Yeah, but let's do the following example. So now this is a problem. Let's take U to be a functor from abelian groups to the category of all groups. Again, this is a forgetful functor, just forgetting that for a group actually that we can, the group that we consider is actually an abelian group. So describe in this case the left adjoint functor. And then all the problems of this kind, you can give an answer, what F is, or you can give a reason why such F doesn't exist.
Okay, we need a functor from groups to abelian groups. So we will take abelianization for group to group factor its commutant. Okay, why is it correct? So,
I think it's supposed to be.
oh yeah, sorry. Yeah, okay, it's equivalent to check that if we have morphism from G from groups to a abelian group, that this initial object in such category, I mean category of objects with morphisms to category, I mean first category. Okay, so because of universal property of factor, always if we have morphism from group to abelian group, every commutant here maps to one here, so we can so we have, because of universal property of factor by commutant, we have only one morphism from abelianization of our group to other abelian group here, so it's initial object in category of morphisms with fixed abelian groups, so it means that
To be
it's
completely formal, we probably need to write something like U of A instead of A, right? To be in the same category of the groups.
oh yeah, no, so it's group abelian and abelian. What's wrong?
No, formally speaking, they live in the different categories, right? So G lives in the category of groups.
Oh yeah. Sorry. Из универсального свойства фактора просто. Ну, у нас, поскольку здесь отображается вот все в единице, то у нас пропускается через фактор по коммутанту.
So the next example is quite familiar to you. So essentially, this is just a pretty way to get a check mark for the solution. So we can consider a category of the pointed sets and forgetful functor to the category of sets. So U in this case is a forgetful functor from the pointed sets, so sets with a distinguished point to just sets, forgetting this point. And again, it's in this sense, there is kind of free construction. There is functor f, which is left adjoint to the U. So what is this functor f? So we can consider pointed objects. So in the sets with a star, so if I want to look at the objects, these are sets, say S, with the x, where x is just an element in this set, and the map between two pointed sets so this was just the map of the sets first of all, and then it maps the distinguished point to the distinguished point.
So consider y is a joint factor. So if there is when or we get this isomorphic to a set of morphism in category of point sets. So,
Wait, it's you're supposed to be the right adjoint,
right,
and you're writing this on the left.
left. I missed the order, yes?
Yeah, so I think the U has to be on the right in the offset and F on the left in the offset.
Okay. So we get this. And
Yeah, it's very hard to read, but that's okay. It's supposed to be sets from the A to the U. In this case, yes, there is a function.
mhm. So I think I just missed the order, so I solved another problem, but
So you found the right adjoint. No, I'm not sure that the right adjoint even exists.
I'm not found the right adjoint.
If you
Нет, ну я просто перепутал немного. Извините.
So if you write it in the correct order, we instead, okay, let's erase this. What we should get? What should we get? F is the left adjoint, so we have let me write it like this. So y comma y is a set y with like a selected point y. It's an element of pointed sets. Is equal, should be equal to sets, and here we have just x and just a set y, because the forgetful functor u just forgets about the exact location of a point y. So how to construct such a functor f? Let us constructed in the following way. F at x is just a set x disjoint union with some specific element, let us call it star. And of course, this particular element becomes like this select point, which is the necessary edit structure. In that case, for each map from f at x to such a pair consists of mapping star to y, and all the other elements of x go to like some elements of y without any restrictions. Trivially, each such map bijectively corresponds to a map of sets x to y, because we have indeed a map from x to y without any restriction. And on the other hand, each map from x to y can be continued to map of f at x to y with selected point y, but by just mapping star to y small. Okay.
So this problem has several variations. For example, there is an algebraic variation where you take forgetful functor from the category of rings, not necessarily commutative, but pointed to just the category, standard category of all rings. So the question is the same. Is it true that there is a left adjoint? And if this is the case, what is this left adjoint functor? То же самое сказать, что под сотом есть какой-то выделенный элемент, морфизм в концах приводит к элемент, выделенный элемент. Ну такая более экзотическая категория. Более экзотическая категория. can try to solve a simple problem with the commutative rings. And then find the commutative from commutative rings to all rings. Okay, so I think we're out of time. And to give you some motivation to finish this problem, this might be one of the problems on the quiz project. So this might be one of the problems on the quiz which will be next week.
А, вам не хочешь?